Hi, everyone. This is Kim Trenbath from the National Renewable Energy Laboratory, and I welcome you to our Better Buildings Alliance Plug-in Process Loads team webinar. I'm just going to go ahead and get started. Thank you all for being here. All right, so for today, we're going to go over some BBA PPL team updates, and then we have two great presentations in line for you. The first one is on device-level plug load disaggregation in a zero-energy office building and opportunities for savings, presented by Bennett Doherty from NREL. And the second one is going to be presented by Bruce Nordman from Lawrence Berkeley National Laboratory on energy reporting, including device demonstration, communication protocols, and codes and standards. After this, we're going to have some time for questions and answers. If at any time you have a question for the presenters, any of us, please go ahead and type that into your chat box, and we will answer all the questions at the end of the presentations. And if we do have time, I would like to reserve a little bit of time for member updates. And so if you want to have, if you would like to present an update, please raise your hand, and if we have time, we'll get to those at the end. So moving on to team players, you see a picture of myself and my team. I'm at the top there from NREL, and you can contact me and my email and my phone. Also from NREL is Bennett Doherty, and we have our team from Waypoint Energy, Katie Brabel and Carly Burke. Next. And I'm pleased to welcome a new team member. Amy Labar is a research engineer in the Commercial Buildings Group at NREL. Her research focus includes building energy modeling, and she is part of a team developing a platform for energy modeling of the U.S. commercial building stock. Ms. Labar earned her MS in mechanical engineering from the Colorado School of Mines, and she also has a BS in mechanical engineering from the University of Portland. We're pleased to have Amy on the team. You'll hear from her a little later You'll hear from her on the next call. All right, next slide, please. The BBA PPL team's overarching goal is to contribute to making U.S. commercial buildings more efficient through plug-in process loads. Our overarching goals break down into working to reducing energy use of PPLs and also working to make PPLs more grid interactive in order to achieve load balancing on the electric grid. We are addressing these goals through two primary approaches: research and applied approaches. Our research goals are to push the boundaries, or what is already known, of commercial building PPLs, and to investigate new technologies that will improve PPL efficiency and grid interactivity. And our applied approaches include encouraging building owners to improve PPLs using methods that are supported by research. These approaches include our webinars, resources on the BBA PPL website, and interactions with you. Next. There are many ways to get involved with the BBA PPL team, and we're definitely interested in collaborating with everyone that's on the call. Getting involved will allow you to stay up to date on the latest research and resources. The first way to get involved is what you're doing right now, participating in the biannual technical calls and any kind of follow-up that occurs. And we occasionally have in-person collaboration opportunities at conferences, so we would love to meet you there. And please reach out to share your updates and best practices so that we can compile them and communicate these through resources. A lot of our resources are found on the BBA PPL webpage, and there's a link to that here. And if you're not sure where to start, please contact us at ppl@waypoint-energy.com. These slides will be available after the call so that you can have access to these hyperlinks. Next. Now I want to give a little bit of an update on some of the more recent things that we are working on. We're currently working on a technical report on emerging technologies for plug load management systems, specifically technologies that learn the occupant behavior and adjust controls accordingly, as well as technologies that allow for better plug load management through automatic and dynamic load detection, or ADLD. ADLD allows for seamless plug load management no matter where the load is located. Next. Our most recent journal publication was in Energy and Buildings in October 2019. In this paper, we talked about our research on device-level load disaggregation, and Bennett Doherty will be presenting on this momentarily. Next. As I said earlier, we have several resources on PPLs and PPL controls available to you through our webpage. Our featured solutions are on the main page halfway down, and this is a screenshot of some of those featured solutions. I want to bring your attention to two of them. The one that's the first blue arrow is how-to guidance on assessing and reducing PPLs in the office buildings. And then the second one is a regularly updated list of utility incentives related to PPLs. This list, which is in Excel format, can be found at the hyperlink above. Next. We collaborate with the Pacific Northwest National Lab, PNNL, on their integrated lighting campaign. The integrated lighting campaign is an opportunity for you to demonstrate or show any work that you're doing to integrate your plug load controls with your lighting controls. They're integrated, these are innovative categories. If you are interested in learning more, please contact Felipe Leon at integratedlighting@pnnl.gov. Next. So there's a couple upcoming events that I would like to highlight on this call. The first one is the BTO Lighting Workshop, which is going to be held in San Diego next week. NREL will be attending this workshop because current building integration efforts include integrating lighting and plug load controls. So we're hoping to collaborate with the lighting researchers and eventually the lighting industry. So if you are attending this lighting workshop, please send me an email so that we can meet up. Next, please. And I also want to highlight the 2020 Better Buildings Summit, which is going to be June 8th through 10th in Arlington, Virginia. The registration is now open and early bird discounts are available. Next slide. And here's a slide that has a snapshot of some of the upcoming Better Buildings webinars, and we encourage you to attend as many as you can because they cross many sectors and many different technologies. Next. Great. Now we're going to get into the technical presentation section of this call. And the first presentation is going to be by Bennett Doherty. Bennett Doherty is a research engineer in the Buildings and Thermal Sciences Center at NREL. His interest in building science began as a participant in the Department of Energy's Race to Zero Now Solar Decathlon Design student competition. During this competition, his team designed a zero-energy elementary school. He then participated in the Science Undergraduate Laboratory internship at NREL, and his work during this program served as the basis for this disaggregation study. Now he continues to work with the Plug and Process Load team in the Commercial Buildings Group and the Building America program in the Residential Buildings Group at NREL. Now I'd like to pass it over to Bennett.
Awesome. Thanks, Kim. Thank you for the introduction. As Kim said, my name is Bennett Doherty, and today I'll be talking about our plug load disaggregation study that was recently published in Energy and Buildings. And next slide, please. So in this presentation, I'd like to talk a little bit about the motivation behind the study, explain the process that we use, and discuss some of our findings. And as some background, plug loads are accounting for a growing percentage of the energy consumed in buildings, especially in high-performance buildings. And the purpose of this study was to explore a method for getting a better understanding of how plug load devices are consuming energy in a commercial office building. So next slide, please. So traditionally, building energy consumption is metered using a single meter that captures the energy consumed by the entire building in aggregate on the left here. Some buildings, however, are designed so that the electric panels are grouped based on end use. And these panels can be metered so that you're able to see the building's energy consumption broken down by end use. So that's the case here on the right. This is an example from NREL's research support facility, which was the focus of our study, as I'll be talking about in more detail soon. So building level submetering is a great first step because it starts to uncover what is consuming energy in more defined groups. However, in the case of plug loads, it still leaves a lot of questions unanswered. Next slide, please. So it would be great if you could take that plug load submeter information and break it down to the level of individual device energy consumption. And next slide, please. Furthermore, instead of just looking at energy consumption, you can also look at power and look at power consumption over time. So that way you can get an understanding of when specific types of devices are consuming energy. Having access to this type of information would allow building managers to better understand which devices to target for energy savings. But the question still remains of how to actually access this device level consumption information. So next slide, please. One of the most accurate and reliable methods to get device level energy consumption information is to use smart plug metering and control receptacles. These plug in between a device and its outlet, and it can monitor a device's power consumption. The one pictured here to the left is the one that we used for this study, and it's called an IntelliSocket from IBIS Networks, and it measures the device's power, energy, voltage, and current, and wirelessly reports that data back to a main dashboard, from which the data can be pulled for analysis. Next slide, please. So theoretically, if we want to know about the energy consumption of all the devices in the building, then we could put one of these smart meters on every single plug-in device, and you have all the information you could ask for. But with thousands of devices in large commercial buildings, metering every single device would be a very costly and very labor-intensive endeavor. So next slide, please. Instead, what if we meter only a subset of the devices to get an idea of how different devices are behaving? And then if we can take a device inventory, we might be able to use that to extrapolate the subset of devices to the rest of the building. If that extrapolation method can work, then we could get a much better understanding of the building's plug loads while only expending the cost and labor for monitoring a relatively small subset of the devices. And so this study, therefore, is a first attempt to see if that method can work. Next slide, please. So the research questions that follow from that are how can limited individual device monitoring and building level submeters be used to develop a disaggregated breakdown of the plug loads in an office building? And what insights can be gained from having a disaggregated breakdown of the plug loads? Next slide, please. So our study took place in the Research Support Facility, or the RSF, at NREL, which is a 330,000 square foot zero energy office building that consists of 3 principal wings that you can see in the top left. There are 4 separate submeters dedicated to monitoring plug loads in different sections of the building. We chose to focus on the B wing east, which is the area highlighted in green at the bottom there. So all of the area in the green is on 1 submeter. All the plug loads are aggregated up to 1 submeter. The B wing east contains the space types listed in the table here, which we have broken up as either workstation spaces, which include open office and private office spaces, where the plug loads are predominantly those found at people's workstations, and non-workstation spaces such as break rooms, copy rooms, and an exercise room. Next slide, please. So in August of 2017, smart plugs were installed throughout the B wing east to monitor the energy consumption of specific devices, as outlined here in this table. This was part of another ongoing plug load study at NREL, so we didn't necessarily decide exactly what was metered, but we were able to use the data for 118 devices from October to December of 2017. We used 5-minute granularity for both the smart plug measurements and the plug load submeter, and we removed weekends and holidays since we were interested in studying the typical workday. Next slide, please. So these are the results that we get for the average workday when we plot the raw data from the smart plug meters. The black line at the top is the plug load submeter, which is, again, that green section from a couple slides before. It's the entire wing, which represents the total aggregate plug loads in the wing, whereas the data in the bottom is from directly from the smart plug meters. So this demonstrates that we have only actually metered a relatively small portion of the total load, but the idea is that if we can take an inventory of the devices, then we could use that to scale this raw data up based on how many of each device type are in the wing. Next slide, please. So to do that, we needed to take a device inventory. So we went around different spaces in the B wing east, counting how many devices we found. We ended up inventorying roughly 70% of the floor space in the wing, and we used these equations to estimate the total number of devices in the wing. For each device type, we came up with an estimate of the total number of devices we expected to find in each workstation space and each non-workstation space. So for the workstation spaces, we took the total number of devices we found, we divided that by the number of workstations we inventoried, and that got us a number of devices per workstation figure. And we multiplied that by the number of active employees in the building, under the assumption that roughly every active employee would have one workstation. And then for non-workstation spaces, we instead divided the number of devices we counted in those spaces by the number of rooms we inventoried. And then we multiplied that by the number of rooms that were in the wing of that space type. So the workstation total accounted mostly for devices that are typically tied to individual employees, like laptops, whereas the non-workstation total accounted for devices that are typically just tied to specific rooms, like projectors. When we add the two together, we get the total estimated number of devices in the B wing east. So next slide, please. So based on those equations, these are our results for all of our metered devices. You can see the estimated number of devices in the B wing east based on those equations. And then on the right, we have the estimated percent of devices metered in the B wing east, basically saying, of all the devices we expect to be in the wing, how many did we actually meter? And this can vary a lot. So for microwaves, for example, we metered 4 microwaves out of an estimated 13 or so, which is a little over 30%. Whereas for coffee makers, we only metered 1 of the expected roughly 10 coffee makers in the wing. And I'll talk a little bit more about the consequences of this shortly. So what we did was take the average daily load profile for each of these device types, and we scaled it by the representative number of devices we estimate to be in the wing. So that way, the disaggregated model represents all of the devices in the wing. Next slide, please. So when we did the inventory, we found that there were a lot more devices than we necessarily had smart plug meters able to meter. So for 7 of these devices, we were able to make estimates for how much these types of devices were contributing to the base load. So for refrigerators, for example, we used some additional meters to measure 3 refrigerators for 24 hours, and that got us to an estimate of roughly 65 watts for the typical refrigerator as its base load contribution. So they certainly consume a lot more during their compression cycles, but since we just were interested in figuring out what their conservative estimate for their base load contribution. One more thing to point out in this inventory, we also came across the central monitoring station TVs. That's a security kind of surveillance area, so there's 15 TVs in there that have to be on all the time. So that's another big load. So next slide, please. So we took those supplemental estimates, and we took the scaled smart plug meter data, and we put all that together to get this final full disaggregated plug load breakdown for the B wing east. So a couple things to note: it matches the shape pretty well. So in the morning, you see this increase. We see a spike midday, and then you see it decreasing through the afternoon. But it also is clear that it doesn't match the full magnitude. So at the top, again, we have the plug load submeter, and you see a gap between the plug load submeter and our disaggregated model. We learned from our inventory that there are many devices that were contributing to the building's plug loads that we weren't actually able to have smart meters for. Some of these devices were small loads, like pencil sharpeners, while others were much larger. And one notable one that we could not access was an ice maker that's running all the time and likely was contributing to this gap. So you can see that the midday spike, this aggregated breakdown lets you see that the midday spike is due to the microwaves at lunchtime, which is because a lot of people in our wing choose to heat their own food for lunch. Sometimes office building plug loads will actually be modeled as having a dip during lunchtime rather than a spike, making the assumption that people will go out for lunch. So basically, this is pointing out that the shape of the plug load profile is very dependent on occupant behavior. And so building-specific considerations should be included when modeling plug loads. One more thing to note is on the left here, we see a spike due to the coffee makers, but that spike's not reflected in the plug load submeter. And that goes back to what I said before about the fact that we only metered one coffee maker out of an estimated 10. And because coffee makers are very dependent, their power consumption is very dependent on when people use them. What that leads to is that when we only meter one and somebody comes in, relatively frequently at the same time of day and turns it on at the same time in the morning, which is a common thing for coffee makers, when we scale that up to 10 different devices, it's as if all of the coffee makers in the wing are coming on at the same time. In reality, there's diversity in their usage. So if we were able to meter more than just one, we would see this spike disappear. Next slide, please. So with this information, we can start to look at some of the devices in more depth. For example, this figure lets us see the plug load profiles for various devices for each day of the week. Here you can see how spiky the coffee makers and the water boilers and the microwaves are as compared to the laptops and monitors. You can also see that the loads are lower on Fridays, as there are typically fewer people in the office on Fridays. That's due to things like alternative work schedules. Next slide, please. So another interesting thing you can look at is you can start to see which devices are correlated with others and which devices are correlated with the plug load submeter, the total plug loads in the wing. So on the left, you see that for the most part, regardless of the plug load submeter power, the desktop server most frequently is around 130 watts, whereas the monitor has a more direct relationship with the plug load submeter, in that the monitor tends to be on during the day when the total plug loads are high, and tends to be off during off-work hours. So that's why we see this more direct relationship. In the figure on the right, we did a Spearman rank correlation test and found that the laptops and monitors are most strongly correlated with the plug load submeter. And they're also most strongly correlated with each other. So this allows you to start comparing which devices are similar to each other in their power consumption profiles, and lets you start to think about how you might monitor devices in the future. So because monitors and laptops are similar, maybe you could meter them together. Next slide, please. So another way to look at this is to say what percentage of the total plug loads does each device account for throughout the typical day. So this graph is normalized so that the plug load submeter value is always at 100%. You can see clearly here that during the day, the laptops and monitors, which is the blue chunks in the middle, make up a large percent of the entire load during the day, but they make up a much smaller percent during the early morning and evening. So I think you can also see that the central monitoring station TVs that I mentioned before and the AV controller have very large chunks, both especially in the evenings and in the early morning. So next slide, please. So we can take that idea a little bit further and dive into it more with this graph here. So we can start to see this type of analysis more clearly when we look at the percent of the load during occupied times, which we define as 9 a.m. to 5 p.m. On the y-axis, and the percent of the load during unoccupied times, which we define from 9 p.m. to 5 a.m. on the x-axis. So everything that falls below and to the right of the diagonal line is taking up a larger percentage of the load during the unoccupied hours than it is during the occupied hours, meaning that it might be a good candidate for controls. And so some of the power behind having this information is that a building manager can better target devices for energy efficiency upgrades or controls implementation. So for example, from this analysis, we found that we could reduce the load during unoccupied times by 33% if we applied controls to turn off all non-essential devices that we metered. And in this case, we're considering non-essential to be things that it's not too risky to turn them off in the evening. So we wouldn't want to turn off a desktop server or a computer because we might lose important data. But something like a desktop lamp or a desk lamp, we could more confidently turn off. But the kicker is that to get 33% reduction, we would need to add controls to 670 individual devices. Now, if we look more closely, however, we find that we can still reduce the unoccupied load by 25% by selectively controlling only 13 devices, including the audiovisual controllers, video conference cameras, and copiers, which is a much more reasonable undertaking. These are the types of insights that can come from disaggregation through the process of metering devices, taking inventory, understanding how devices consume energy, and hopefully someday the type of device energy reporting that Bruce will talk about in a little bit. Next slide, please. So just to summarize some of our key takeaways. So our disaggregation model was effective, but there are still unknowns as not everything was accounted for. And I think I'll throw in there too that this is just one study. We hope that it could be repeated for other buildings to see how effective this is in other buildings, and we would love to have it replicated. The lunchtime peak was due to the microwaves, which is a building-specific characteristic, and those are types of characteristics you have to consider when modeling plug loads. Laptops and monitors are most strongly correlated with the overall plug load submeter. The audiovisual controllers account for a significant portion of the unoccupied load, consuming roughly 1.5 kilowatts constantly. And it's from this disaggregation that we can better target these energy savings. So we can pick more directly which devices we want to target. Finally, in discussion with the RSF's building manager, we learned while there were fairly strong plug load policies put in place when the building was built, over the past 10 years or so, the people and devices in the buildings have changed, and those changes require plug load policies to be updated and reinstated. And there's more about that in the full report here, but I think that's an interesting thing to see how things change over time. Next slide, please. So here are some recommendations for anyone interested in conducting a similar study or something of the similar nature. So at the onset, we recommend it's important to identify and understand all of the devices in the building, and we'd encourage conducting a 1 to 2 week pilot study to get used to the monitoring equipment and to better identify these devices. And this information should help you select which devices to monitor. And we certainly want to focus on major loads and loads with high variance, like what I discussed with the coffee makers, so that we can capture the device usage diversity across the different devices. Through this process, you can take note of high energy consumers, which may end up being good candidates for controls, as long as there's occupant engagement and education, because that's very important for a successful controls campaign. And finally, we can consider unique occupant schedules when analyzing your data, and especially if you're considering setting controls, because every building is different. Occupants change from one building to the next, and it's important to have this be a building-specific process. Next slide, please. So if you'd like to learn more, you can find the full report here. There's a lot more information there. And if you have any questions or comments, you can post them here into this the GoToWebinar panel, or feel free to send me an email directly. And next slide. So finally, I just want to say thank you for listening, and thanks, Kim, for giving me the opportunity to present.
Great, thank you, Bennett. All right, if anyone has questions for Bennett about this research, please type it into your chat box, and we will get to answering these questions at the end of the webinar. All right, next slide. Now I would like to introduce our second guest presentation from Bruce Nordman. Mr. Nordman is a research scientist in the Electronics, Lighting, and Networks group at LBNL. He worked in the computer industry in the late 1970s and joined LBNL a few years later. He has worked on electronics energy use since the mid-90s. For about 20 years, he has focused on the intersection of IT networks with energy use and efficiency. His current research includes physical layer network interfaces, application layer protocols, user interface standards, occupancy detection, and DC power distribution. Now I'm going to pass it over to Bruce for his presentation.
Yes, thank you for that introduction, and thank you to all the organizers for for the interest in this topic and for all of you for your time as well. The topic of energy reporting is really very complementary to Bennett's presentation and is intended to be a way to more easily get more data about devices in buildings to people who want to understand and improve their operation. But critically, it's not limited to just plug loads. It can apply to any device in a building and any building type. So next slide. So I want to thank the sponsors of our research project, which concluded last year, which is primarily the State of California's Energy Commission and also the Energy Star program that has been interested in energy reporting for well over a decade. The project was conducted by LBL and also by a consulting company nearby here in Oakland called Energy Solutions. And the symbol in the top center is a graphic I made to try to symbolize the concept of energy reporting, because it can be sort of abstract, which is the power symbol to represent energy being digitized into information and then being communicated to some other device. And that really is the essence of energy reporting. And in the presentation, I want to cover why we would do it, which again builds off a lot of the reasons why you would do the type of analysis in the last presentation. The fundamental architecture for how it should be done, because there are different ways of doing it, and I believe that this way is really the right way to moving forward. Talk about some actual end-use devices that we collected that do energy reporting today. There's issues with communication protocols and data representations that still need to be worked through. The data needs to get sent to some central management system within the building, and then there's ways that energy codes and standards can help move the concept forward. So next slide. So I like to think of buildings as in some ways being like a black hole in the universe, in the sense that energy goes in and no information comes out. And that's sort of been largely a traditional way the buildings operate. They're very opaque to people. They only see a monthly energy bill, if they even see that. So lots of times people don't really know what's going on. So one of the goals of energy reporting, as with the previous presentation, is to try to break through that and make buildings more transparent and visible as far as their energy use. So next slide. So why would we do this? Well, if people don't know where the energy is going, then they can't find problems or figure out ways that buildings could be operated better. And while one can certainly do the type of monitoring that was described in the earlier presentation, and some people will, and hopefully more of you will do it, the reality is that probably most people won't. And so if we can provide free information that with very minimal effort, we'll reach a lot more buildings and a lot more devices in buildings. So what energy reporting is the idea that every device should be able to track and report on its own energy use. And this should be a free feature of all devices. In future, it should be like a device being safe, where you'd be surprised to go to the store and find a device that doesn't support energy reporting. Now, of course, this requires the device to be able to communicate, but in the long run, everything will communicate. And in general, you would probably very rarely add energy reporting capability to it. You'd rarely add communications ability to a device only for energy reporting purposes, but more and more devices have communication for other purposes. And so once you have that, you can then add a little bit of firmware to the device to track energy use and report that. And so get the feature for no incremental manufacturing cost and no external hardware. So next slide. So this is the architecture slide. So power flows into buildings and ultimately into end-use devices. They consume that power and then keep track of it. Many devices could simply estimate their energy use. So a notebook computer knows if the display is on and how bright it is. It knows how fast its processor is going, how much memory it has, what USB devices are connected. So it can, maybe on a second-by-second basis, estimate the total power and accumulate energy use. Some devices already today measure their energy use coming in, and the incremental cost to do that is dropping rapidly as more and more integrated circuits and power conversion include the ability to simply report out energy use. And there are many devices that have the right circuitry in their power supply, they just don't make use of it. So you use the network connections already there and you estimate it, and that's how you can do this without any new hardware. A key point of how I define energy reporting is that it's only reporting within the same building from the end use device to some management system that receives the information. Today, in some cases, people have devices that report their energy use to a manufacturer's cloud or some other external entity. And if people want to do it, that's fine, but that's outside the scope of how I would define energy reporting, because we want to make sure that people associate this concept with maintaining their privacy and security. So that ideally the default behavior of devices when you buy it in the store is they only report locally. And then if you want to report outside the building, you have to take some opt-in action to make that happen. And then ideally, if you did do any sharing outside the building, you would do that from your central management system so that you only have one device in the building for which you have to have configuration of privacy and security controls, rather than having dozens or even hundreds of devices where you have to configure them all separately. So you really want to make sure that the default is preserving of privacy. And also, as an energy researcher, of course, myself and all the people at NREL would love to have this data so we can understand energy use. And we could certainly set up mechanisms so that anonymized data gets reported, so that you could see how much energy is used by all refrigerators of a certain brand, model, and manufacturing year to understand how things are performing over time. But you don't want to get just a string of energy values. You also want to know what this device is. So you want to know its brand, its model, its location within the building, other information. And it turns out that's actually really ultimately the most complicated part of the whole energy reporting process. Also critically, the management system, this receiving entity, pulls the data as often as it wants to from the end use device, so that the end use device is as simple as possible for energy reporting. It doesn't keep track of time series data, only the management system does. And there's a whole variety of advantages to this kind of architecture versus having the device keep track of time series data. So next slide. So devices for sale that do energy reporting have actually been around for a long time. There's not that many of them today, but every year there's more and more. And this is a list I actually made several years ago of devices that are known to support energy reporting. The image on the right actually is from some software for my notebook computer. There's all kinds of sensors inside the computer that that Apple generally keeps to itself, including 4 voltage measurements and I think it looks like 8 current measurements. So there's actually a lot known about the power going inside the buildings already. It's just usually trapped inside of it. So what we're really often doing is just liberating information that already exists. Next slide. So as I mentioned, for this project that is now since concluded, we created a collection of about a dozen devices that do energy reporting, reported their data to a management system, and showed it at a variety of meetings and conferences. Some of them were products that you can buy today. Some of them were products that we had the manufacturer modify to add the feature. And then in one case, we just modified the device ourselves to add software to a notebook to do energy reporting. Next slide. The concept is really, and as I mentioned, you can either measure or estimate the data, and it really doesn't matter. Part of what you also want to report is how accurate the data are. So some devices might be down to 0.5%, or maybe some devices are only plus or minus 5%. As long as the device reports the accuracy, it's much less important how accurate it actually is, because then you can interpret the data correctly. So yeah, we had measured, estimated, and in 2 cases, we just got device status from the device, and then within the management system, translated that status into power and then energy use. Next slide. So as I mentioned, the concept of energy reporting is applicable to any device in the building that consumes energy. We only focus on electricity, but you could also apply this to other forms of energy, from HVAC to lighting to electronics. And we also included several external meters in the project. Actually, the one at the bottom center is the size of a postage stamp, and you just plug an electrical outlet through it. It's only about a 1/16 of an inch thick, and it chirps out the data over Bluetooth. It's a pretty impressive device called a power blade. So next slide. So once a device can communicate, then you can not only get information from it, but you can send control commands to it. So for two of the devices that we had the manufacturer modify, we actually had them be able to take in price signals and modify their behavior based on prices. So at higher price levels, they would cut back on power by either, in this case, dimming a light or reducing the fan speed on an air purifier. To demonstrate the price-based control is quite possible. For other devices, they couldn't take in prices, but they could take in other network commands to control their behavior. So in a lot of cases, you may get energy reporting data that suggests how to better control devices, and these devices already have that capability built in. So next slide. So from this collection of devices, that we really believe that any device that can communicate can readily do energy reporting. We did test the accuracy of all these devices, and it was certainly varied, but in all cases, it was good enough for decision making about energy use and understanding energy use patterns. The communication protocols these devices used were quite varied, but in cases where they use standard protocols, it was much easier because it was easier to integrate. And then once you'd integrated one Zigbee device, the next one was much easier. And ultimately, this all needs to be quite plug and play, completely automatic, so that there's no configuration needed at all. Now, the most challenging part of this was actually not the energy data, but the other metadata associated with the device, such as brand, model, location, etc. This kinds of information is often absent from protocols, or it's in the protocol, but the devices don't use it. And that's definitely the place where we need the most work to improve the technology of energy reporting. And ultimately, from our understanding and from working with the manufacturers that we had modified products, it's really not that difficult to do this, because if you're not adding hardware, you're not adding new communications, the incremental effort to keep track of energy use and reported is not great. So next. So as I mentioned, this metadata, this static data on the devices was the most problematic. So for what we did is surveyed many dozens of protocols and identified the types of information which we thought were really most useful and important and relevant for energy reporting. And so created what we call a reference data model, with the idea that you could take data from any particular protocol and translate this into some standard form. And then over time, you could harmonize protocols towards the standard data model, and maybe even have new protocols use it directly. So we have consistent naming and representation of information, which is the same information. And in this list, you can see that actually there's only two of the rows which are the actual energy data for power and energy. The rest of it is all this metadata about related information. Now, some of this actually isn't even the direct energy reporting data, like we specify temperature and occupancy sensing, because as long as you're collecting this data, you might as well collect other data that the device might have. And an increasing number of devices do have these sensors, and it's just a lot easier to maintain sensors if they're part of a device rather than a standalone device that has to be installed and maintained and communicated with. So next slide. So ultimately, we really would like to standardize this reference data model, and there is an ANSI CTA standard called 2047 on this topic, which we're hoping to move this information into. And this really facilitates moving information between protocols, because while ideally all devices and buildings would use one protocol, that's not the future we're going to have in the near term. So we do have to have these gateways and translations between protocols. But we would like to minimize the number of protocols in use. And there are two efforts that are aiming to do that, at least in the residential sector. The one on the left has been active for just over a year, and the one on the right just over a month. And as you can see, there's a lot of big companies involved in these. And so I'm cautiously optimistic that we actually may get to much greater interoperability between devices, at least in houses, over the coming few years. And then hopefully that can then translate over to commercial buildings for interoperability more general, of which we hope to bring energy reporting and energy concerns into these processes. So next slide. So as part of our demonstration, of course, we had to have some device that collected the information. So we wrote PC software that used a variety of different protocols to query our device collection and collect the data, translate into a common format, and be able to display it graphically in different ways. This is not intended to be a production system that we would share with others, although if hopefully someone on this call wants to create such a system that could be freely available, much like early web browsers were developed by universities and shared, and eventually other organizations created better and faster web browsers, but having that initial free version was essential to popularizing the concept. There is one outstanding technical issue, which is how to make sure the devices by default don't respond to requests outside the building, network, and that's a topic I'm continuing to try to work on to figure out how we can make sure that the default is to limit data sharing. So next slide. So as I mentioned, energy codes and standards can certainly help move this process forward. Energy Star has been anxious to help encourage energy reporting, and once there's enough products that can do it, they could potentially actually require energy reporting to be a feature of devices to get the Energy Star label, and I think that's the direction we should look to. And building codes and appliance standards similarly could either reward or require this capability. And again, ultimately, we really want to get people have the idea in their head that this should be a standard feature of devices. And the report that was written up for this project has a lot of detail on this and other aspects of the project. So next slide. So what can we use this data for? We can use it for understanding energy use, but you can also use the data for building tenants, or if suppose you've got some vending machines in the basement and you want to make sure that the machine owner pays for the energy they use, so they have an incentive to make it their device efficient. A lot of buildings, their actual consumption significantly exceeds their designs, and so this can help understand that. And you can also simply track devices for reasons unrelated to energy at all. So it's really a very handy feature. So next slide. So next steps, there are some steps to improve the technology and make it more streamlined, and that's something I hope to continue working on in the coming years. And probably some of you could also help do that. Also, I'm hoping that a number of you on this call actually can go out and try to find find products in your buildings that can do this and start doing some initial collection of data this way, and combine it with external meters as was described in the earlier report. Most devices today don't do energy reporting, so we will need to make good use of external meters for a long period of time, but hopefully over time, more and more devices can simply do this natively. And as more devices become available, then you can announce that, hey, we're only going to buy products that do energy reporting to make sure that manufacturers get that message that they should put it in their products. So next slide. So again, thank you for all your time and attention, and please feel free to reach out to me with questions or comments. The bottom URL is a web page for this project in general, and I will seek to get this final project report posted there. But if you don't see it, email me, and I can make sure you get it in the meantime. So thank you.
Thank you, Bruce. That was an excellent presentation. And a lot of the work that Bruce and his LBNL team completed really solidifies the foundation on which future technologies can build upon, especially when it comes to the energy reporting and other use cases that might need to know the energy use of the individual devices. So thank you very much for your presentation. Next, we're going to move into the Q&A part. So we have a handful of questions that have been listed for the first presentation that Bennett gave. And I just want to remind everyone on the call, if you have questions for the second presentation that Bruce gave, please type them into your chat and we will get them organized and ask them to Bruce on the call. So I would like to start with the first question for Bennett. Have you thought about plotting loads versus solar output, like the cost of energy? Future smart buildings will incorporate more than conventional load reduction. And this question is from Tim Elliott. So thank you, Tim. Bennett?
Yeah, sure. So that's a really good question. I think it maybe was a little bit outside the scope of this specific study, but I think that it's definitely something that a future, you could look at in the future. So I think the idea here being that if you did have this kind of disaggregation, load profile, you could also start to look, you could overlay that with exactly what was said here, the solar output. You could overlay that with cost of energy as it changes at different points in the day, and you can then start to compare, okay, when the energy prices are high, these are my specific devices that are consuming a lot of power. And so you could start to see which devices are costing you more. And this is I think this is a great idea that could be extended well beyond plug loads to other end uses as well. But if you have this disaggregation and you could overlay that as well, I think that's a great idea for tying, how much does it actually cost me to run all of these devices, specific devices. And I think that could be really interesting moving forward. So that's a great idea, and I think that's something for us to think about too if we come back to it.
Great. Thanks, Bennett. I have a second question for you.
Sure.
Do you think the energy data you gathered from the various devices during your study could be used to predict which type of device is plugged into a given outlet? And is a device's energy consumption too dependent on occupant behavior to do this reliably?
Awesome. So that's another great question. And I think this is an area that's been actively researched for a while. It's something that we even looked into a little bit to learn about from some of our research this past summer. And I think that some might call this non-intrusive load monitoring, or keeping track of using electric signals to kind of determine what the device is. And I think that there's a lot of work being done there, and for some devices it definitely is possible, ones that have unique electric signals. But there's also, it's also very difficult. I haven't done it myself, but from what I've read, it seems that there's a lot of different ways you can go about doing it to actually be able to confidently identify devices. And to have these high accuracies, you also tend to need pretty significant detail in your metering capabilities and your computing capabilities for processing after the fact. So from what I've seen so far, I think there are definitely companies that are working on it and companies that are doing really great work to get there. I don't know that you can confidently say that you can actually predict what each device is just based on its signal there. But I'm hopeful that more work will be put in that direction. So that's another great question.
Okay, great. Thanks, Bennett. Okay, I'm going to ask two questions of Bruce. And then I also want to remind the audience, I think we might have some time at the end for audience updates. So if you feel like you would like to share some information, please raise your hand on your panel, and when I do the member updates, I will open up your line. So Bruce, for the first question is, of the many ways that you were able to get these devices to report this information, were there any that you think worked the best, recognizing that this was not a recognizing that this was not at a production scale?
Yeah, so our management system was not production, but some of the devices are devices you can buy in the stores today. So this is real technology. I would say that in some cases we had to go through a gateway to go from internet protocol networking to some other physical layer, and obviously if you can just stay in IP, then that's going to make things simpler, and we certainly found that. I would say that as far as particular protocols, the Zigbee application layer and simple REST APIs both were quite simple to work with. But ultimately, once we end up with maybe 3, 4, or 5 protocols that are in common use for this purpose, the management systems will implement all of them, and it will be not particularly burdensome. So it's just a matter of getting down to a few. It's much less important which few. And then as far as, oh yeah, and was there a second question?
Okay, great, thank you. Okay, so the second question is, do you think adoption of this, what do you think adoption of this would look like if it were pushed through the standard process?
So there's 2 different standards processes potentially in play. There's the technology standards and the energy standards. For the technology standards, as I mentioned, it's trying to harmonize the various different protocols towards a common way of representing the information and defining unambiguous translations between them, so we can move the data to a common format in between the protocols. For the energy codes and standards, certainly it's something that we'll have to see good uptake in the market before one could push that through. And again, I foresee it being specifying the device must support one of some small number of protocols. We're not going to get to a single protocol for this purpose, I don't think, at any time soon. And again, this would be for devices that can already communicate, so that you don't impose a hardware cost burden on the devices.
Okay, great, thank you. I have one general question that came to me, and it is, how do we get a copy of the presentation? It's a nice, easy question. Our team will send out the presentation after this call to the people that have attended the call. So that's where you'll get a copy of the presentation. Also, we're posting this webinar online. It'll be on our PPL website. So there'll be a link to the webinar, and then also a link to the presentation online as well. At this point, I would like to, I do not see anybody's hands up for a member update, so I'm going to move into the closing. I want to thank everyone for joining our call. We greatly appreciate your time. We are also looking to continue to build the team that works on plug loads and PPLs. So please, if you have any questions, please contact us. Our email is ppl@waypoint-energy.com. And if you are conducting any work in this space, we're interested in talking to you and trying to find synergies between potentially your project and others that are doing similar work, so that we can share best practices. And so with that, I want to thank you all for joining the call, and we look forward to being in touch. So have a great rest of the week.